ChatGPT designed a messaging app architecture in 3 seconds. Clean code, REST APIs, HTTP polling, a solid Postgres schema. So what exactly is your job now? Here is what it did not do. Look at WhatsApp scale, 100 billion messages delivered every single day, and say HTTP polling will crash the servers. We must maintain 2 billion persistent WebSocket connections using Erlang OTP. That judgment call, made before a single line of code is written, is the one that kept WhatsApp from collapsing. After this video, you will be able to make it and explain exactly why. That is the skill that survives. 5 things you will own after this video. Why REST APIs and HTTP pooling collapse under WhatsApp's load with exact mechanics, not theory. Why WhatsApp chose Erlang OTP and rejected Java or C++. The XMPP backbone using Ejabberd for long-lived WebSocket connections. The trade-off AI misses when asked to design this, and the survival skill, naming the constraint before naming the structure. If you watch this video to the end, you will be able to answer a chat system interview question better than 99% of candidates who have been building software for years. Let us start with what breaks. Imagine asking someone a question by calling them on the phone every 3 seconds just to see if they have an answer, that is HTTP polling. To get real-time messages, the app sends an HTTP GET request to the server repeatedly. Any new messages? Any new messages with 2 billion users polling every 3 seconds. The system processes over 600 million requests per second. The API gateway routes these to the HTTP server. Standard web servers like Tomcat or Nginx use a thread or process for every request. Creating and destroying a heavy operating system thread 600 million times a second immediately exhausts system resources. CPU context switching pegs the server to 100%. The server freezes before a single message is ever sent. Worse, the HTTP server hits PostgreSQL to check for new messages. 600 million SQL queries per second. You have accidentally executed the largest distributed denial of service attack in history against your own database. The REST API approach breaks at WhatsApp scale before you add any other feature. This is the problem that forces a different architecture. Not because REST is bad, because the concurrency constraint makes HTTP polling physically impossible. That constraint is the entire reason for everything that comes next. Instead of hanging up and calling back every 3 seconds, imagine picking up the phone and just leaving the line open indefinitely. When someone speaks, you hear it instantly. That is a persistent WebSocket connection. The client connects once, and the server pushes messages down that open pipe. The millisecond they arrive, no polling, no database hammering, but keeping 2 billion connections open requires servers to hold state. A typical Java or C++ server can hold maybe 50,000 concurrent connections before the operating system runs out of memory for heavy threads. WhatsApp needed more. They needed to hold 2 million connections per server. This is where the Erlang programming language and OTP framework come in. Erlang does not use operating system threads. It uses ultra-lightweight, green processes managed by its own virtual machine. An Erlang process takes 300 bytes of memory. A Java thread takes 1 megabyte. Erlang's actor model means processes do not share memory. They just pass messages to each other, completely eliminating deadlocks. Using a customized Ejabberd XMPP server written in Erlang, WhatsApp handles over 2 million concurrent persistent connections on a single machine. Every architecture trades one thing for another. Erlang is terrible at heavy computation, image processing, or complex math. If you try to run machine learning in Erlang, it will crawl. But WhatsApp does not do math. WhatsApp takes a small encrypted message from user A, looks up user B's open connection, and routes the message to it. That is it. For routing millions of concurrent messages without crashing, Erlang is unbeatable. That is the constraint-based reasoning that separates a developer from an engineer. The developer sees an obscure language. The engineer sees the only runtime environment that fits the concurrency budget. Now, how does WhatsApp actually wire this up in production? let us look at the flow. WhatsApp's backend is a fleet of Erlang chat servers. When you open the app, you establish a persistent TCP or WebSocket connection. The chat server holds that connection open in memory. User A sends a message. It flows over their already open connection through the load balancer. The load balancer routes the message to the specific chat server currently holding user A's connection. The Erlang chat server looks up user B. If user B is connected to the same server, it pushes the message immediately. If user B is on a different server, Erlang's built-in message passing routes it across the cluster in milliseconds. The message is pushed down user B's open WebSocket connection. Zero polling, zero database queries in the critical path. The message is delivered. If this kind of judgment call, picking Erlang and WebSockets over HTTP because the concurrency budget demands it, is what you want to make confidently, subscribe now. Every Tuesday, one system design judgment call, free. HTTP servers use heavy OS threads, capping out around 50,000 connections per server before memory exhausts. Erlang processes are tiny, allowing over 2 million persistent connections on a single machine. At 2 billion users, polling generates 600 million requests per second, executing a DOS attack on your own database. WebSockets push messages instantly the millisecond they arrive, requiring zero database reads for online users. Ask an AI to implement a chat app and it generates a REST API, logically correct, completely unscalable at 2 billion users. The engineer defaults to the constraint. The answer is not WebSockets because they are real time. The answer is the concurrency constraint of 2 billion active devices makes HTTP overhead impossible. That answer is the one that gets you hired. Let us put it all together one final time. The full system in one clean view. Full system, every component visible, zero HTTP polling, total delivery time under 50 milliseconds. Here is the complete path and why Erlang makes it possible. User types a message. The payload is end-to-end encrypted on the device. It travels over the open WebSocket to the gateway. The gateway forwards the TCP stream directly to the Erlang chat server managing user A. The chat server needs to know where user B is. It queries a Redis session cache, which server holds user B's open connection. Redis instantly returns the ID of the chat server managing user B. Using Erlang's distributed message passing, the payload routes directly to user B's server and is pushed down their open WebSocket. Delivery complete, zero database scans. Millions of these happen every second. Before this video, the answer to how does WhatsApp work was they use WebSockets. After this video, the answer is 2 billion users polling an HTTP server causes thread exhaustion. WhatsApp uses Erlang OTP and a customized XMPP server to maintain 2 million lightweight processes per machine, allowing them to push messages instantly without touching a database. That shift is the judgment call that no AI prompt can generate. That shift is your job. You now own the architecture. Last piece. How do you walk an interviewer through this in 45 minutes? That is next. 45 minutes, blank whiteboard. Phase 1 is clarifying constraints. Ask for the daily active users and the concurrency peak before you even mention a database. 2 billion users changes everything. Phase 2. Propose the naive approach. Say out loud that an HTTP REST API with polling will cause thread exhaustion and run the math to show why the server will crash. Prove you know why it fails. Phase 3. Introduce WebSockets or TCP. Explain how maintaining state on the server eliminates polling overhead and database DDoS attacks. Phase 4. Concurrency. The interviewer will ask how a single server can hold millions of connections. Your answer is Erlang OTP or Go-routines, lightweight green threads that don't exhaust operating system resources. Finally, phase 5, the trade-offs. Acknowledge that keeping connections open requires massive RAM and complex load balancing, but dismiss it as the mandatory cost of achieving real-time delivery at a 2 billion user scale. Before this video, WebSockets are fast. After this video, the 2 billion user concurrency constraint makes HTTP polling physically impossible. Persistent connections and Erlang lightweight processes are the only structures that fit. The engineer who can say that in an interview, in a system design discussion, in a code review, that engineer is the one who built the system. Everyone else wrote the REST endpoints after the decision was made. That distinction is your survival skill. Next Tuesday, message delivery and receipts. The famous single tick, double tick, blue tick. When 2 billion people type at once, how do you guarantee order? The AI default relies on client timestamps, which means your messages arrive completely out of sequence. An engineer uses centralized monotonic sequence generators. That is episode 2. The architecture that guarantees your messages actually makes sense. Subscribe to ByteLearn for the complete one engineer system, WhatsApp edition, one system design constraint per week, every Tuesday. If you are a B.Tech student, a fresher, or an engineer wondering how to survive the AI era, this series is the answer. Hit the bell. See you Tuesday. Question: which architecture judgment surprised you most? The thread exhaustion trap. Drop it below. I reply to the first 10.